Welcome you all in the lecture number 13 of Abstract Algebra MTL 6051. In this lecture, we will going to prove Cauchy theorem. What is Cauchy theorem? If G is finite group and P divides order of G, then there exists an element in G such that x to the power P is identity. What it means? G be a finite group and P divides order of G, right? If P divides order of G, then there exists an element, say x, in G such that x to the power P is identity, right? We have to prove it, okay? How we will prove it? To prove Cauchy theorem, we apply the method of induction. Method of induction on what? Method of induction on order of group, okay? Let G be a finite group. Let G be a finite group and order of G is small n, right? This we are assuming that order of G is small n. Since G is finite, so its order exists and say it is small n. Right? Apply method of induction on order of G to prove Cauchy theorem. If order of G is 1, let us assume, then result is true. Order of G is 1 means G containing only identity element. Okay. Then e to the power P is always identity. Then result is true. Now, then what method of induction says that? Method of induction says that if result is true for k equal to 1, let us assume that result is true for all numbers s which is less than k. Right? Method of induction says this. Then by method of induction, assume that the result is true, means this result is true for all those groups whose order is less than order of G. Okay. If any group H, suppose any group H such that order of H is less than order of G, then there exists A belongs to H such that A to the power P is identity. Okay. It means by method of induction we are assuming that this result is true for all groups whose order is less than order of G. Okay. Now assume two cases. G be a group. G is a group. Then this group is maybe cyclic or not cyclic. Okay. Then consider that if it is cyclic, right? If it is cyclic group and having non-trivial subgroup. Okay. This having no non-trivial subgroup. It means suppose G doesn't possess any non-trivial subgroup. It means what? G is something like ZP. ZP is group with respect to addition modulo P, where P is prime number. This is group. This group is cyclic and its subgroup is 0 and ZP itself. It means non-trivial subgroup. ZP does not containing any non-trivial subgroup, right? G is, in this case, G has no non-trivial subgroup, then G is cyclic. Okay. In such case, if P divides order of G, then order of G must be P. Right? Only in this case, if P divides order of G, then order of G must be P. Okay. If order of G is P and G is cyclic, it means there exists one element. Since G is cyclic and order of G is P, then there exists an element whose order is P. That is, order of X is P. Then X to the power P is identity. Okay? Means result is true if G has no non-trivial subgroup. Okay? Again, assume that G has non-trivial subgroup. In earlier case, we discussed that G has non-trivial subgroup, right? Let us assume that G has trivial subgroup, non-trivial subgroup, say H. Then what is H? H is not identity and H does not equal to G since H is non-trivial subgroup. Okay, non-trivial subgroup of G. Okay. Then what method of induction says that since H is non-trivial subgroup, so order of H is less than order of G. But our method of induction says that this result is true. Which result? Means there exists X belong to G such that X to the power P is identity. This result is true for all group whose order is less than order of G, right? Since order of H is less than order of G, therefore, since order of H is less than order of G, therefore, by method of induction, right? By method of induction, there exists X in H such that X to the power P is identity. Okay, X to the power P is identity. Okay, since P divides G, right? Since P divides order of G, right? Then there are two cases arise. Either P divides order of H or P does not divides order of H. Okay. In first case, if P divides order of H, then this happens. But if P does not divides order of H, in this case, then see. Right? If P does not divides order of H, then P divides order of G by H. Why? Since order of G is equal to order of G by H into order of H. Since P divides order of G, therefore P divides order of G by H into order of H. Since P does not divides order of H by this thing, then P must divides order of G by H. If this thing not happen, it means P does not divides order of G. But we know that P divides order of G. This is the statement of the theorem. Okay. Then P divides order of G by H. What is order of G by H? Order of G by H is less than order of G. Right? P divides order of G by H, and order of G is less than order of order of G by H is less than order of G. Then since order of G by H is less than order of G, and we already assume that by method of induction the result is true for all subgroup whose order is group whose order is less than order of G, means this result is true for G by H also. Then there exists HY. Why? Since result is true for G by H, for this G by H result is true. It means there exists HY belongs to G by H, since the element of G by H, what is the element of G by H? Either AH, either left coset or right coset, such that A belongs to G. Element of G by H is like this, HA. right? Since G by H result is true for G by H whose order is less than order of G, then there exists Hy belong to G by H such that H Y P is equal to H. Why H? Since identity of factor group, identity of G by H is H. Therefore, HYP is equal to H, right? But we know that HA2 is equal to HA2, right? Like this, what is HYP? HYP is equal to H, and this implies that, and also we know that HA is equal to H implies that A belongs to H, okay? This implies that YP belongs to H, this thing, right? If HPY is equal to H, what is HYP is equal to H, what is HYP? HY to the power P is equal to H, but we know that HA is equal to H implies that A belongs to H. This implies that YP belongs to H, right? Next, the YP belongs to H, but what is order of H? We don't know. Say it is T, right? Say this is T. And if A belongs to H, then we also know that A to the power P, T is identity. What is YP? YP belongs to H. What is YP? YP belongs to H. Then this YP to the power T is equal to identity, and this written as YT to the power P is equal to E, and this implies that order of, suppose order of A to the power K is identity, right? Then this K divides order, right? Then this order of Y to the power T, order of Y to the power T must divide P, okay? Then what is order of T? It is, there are two possibilities, either it is 1 or it is P, okay? If this divide P, then there are two possibilities, right? Next assume that order of Y to the power T is 1, right? Let order of Y to the power T is 1. Then this, what is YT? YT is just like identity. It means HYT is equal to H, right? Since order of YT is 1, and what is order of H? Order of H is 1. Then HYT is equal to, what is order of YT? This is 1. It means, what is order of identity? That is 1. This YT is like identity. Then what is HE? HE is equal to H. Then what is HYT? This is equal to H. This implies that order of HYT is equal to H means HY whole to the power T is equal to H. This implies that order of HY divides T. But what is T? Right? This order of HY is P, and what is T? T is order of H. Okay, it means P divides order of H. This is contradiction. Why contradiction? Since we already assumed that P does not divides order of H. We already assumed this, but here it shows that P divides order of H. Why this contradiction? This, since contradiction arises by assuming that order of Y to the power T is 1, right? Then order of Y to the power T is 1 is not possible. Then there are only two possibilities for order of Y to the power T, that is 1 or P. This is not possible 1. Then what is order of Y to the power T? It is P. Okay. It means result is true for this also if P does not divides order of H. Okay. Again, let G is any group. Then apply method of induction or order of G. Order of G is equal to 1, result is true. Suppose the result is true for all subgroup of G also, right? If T is any subgroup of G, assume that T is any subgroup of G, then there are two cases arise. Either P divides order of T or P does not divides order of T. Means either P divides subgroup of G. Don't say this. This is order of subgroup of G. Okay? And P does not divides order of subgroup of G. Either P divides order of subgroup of G or P does not divides order of subgroup of G. Right? If P divides order of subgroup of G, then by method of induction result is true. If P does not divides order of subgroup of G, then apply class theorem. What is class theorem? Order of G is equal to order of ZG plus summation A does not belong to ZG, order of G divided by order of ENA. Okay? What is ENA? ENA is subgroup of G. Apply this thing. ENA is subgroup of G. If P does not divides order of ENA. Okay? Sorry. If P divides order of if P it's okay. If P does not divides order of ENA, then P divides order of G by order of ENA. Why? Since P divides order of G and order of G is equal to order of G by ENA into order of ENA. That is, what is the result? If P divides AB, implies that P divides A or P divides B. Okay. Since P does not divides order of NA, then P must be divides order of G by NA. If P divides order of G by NA, then P also divides summation over order of G by order of NA for A does not belong to ZG. Okay. Then P divides this. Okay. P divides order of G and P divides A does not belong to ZG, order of G by order of NA. If P divides A and P divides B, implies that P divides A minus B also. P divides A, P divides B, then P divides order of G minus summation over A does not belong to ZG, order of G by NA. Okay, it means P divides order of ZG. It means ZG equal to G. Okay, that is G is abelian. Okay, then there exists x belong to G such that x to the power P is equal to E. Hence the result is true. Right? This is the complete proof of the Cauchy theorem. Okay, but what is the application of Cauchy theorem? See one example. For an abelian group, right? For an abelian, we are talking about only abelian group. Order PQ is cyclic. Suppose G is abelian group. Okay, what is G? G is abelian group. What is order of G? Order of G is equal to PQ. What is relation between P and Q? P and Q are relatively coprime. Okay, relatively prime. They are coprime to each other. Then this P divides order of G. By Cauchy theorem, P divides PQ. It means P divides order of G. Then there exists A belongs to G such that order of A is equal to P. Okay. Similarly, Q divides order of G. Then by Cauchy theorem, there exists B belongs to G such that order of B is equal to Q and P and Q are relatively prime. Since G is abelian, therefore AB is equal to BA. It implies that order of AB is equal to PQ, right? That is order of A into order of B, right? Which is PQ. Since there exists one element AB whose order is equal to order of group, it means G is cyclic, right? It means every group of order PQ, right, is cyclic group. See the remark. A group of order 6. What is 6? 6 is equal to 2 into 3. This is P, this is Q. P and Q are prime. What is GCD? GCD is 1, right? This result is satisfied. It means group of order 6 is cyclic. Okay. Now, but the group is abelian. If it is abelian, then it is cyclic. Okay. A group of order 10, which is abelian, this can be written as 2 into 5. This is P and Q. What is GCD of PQ? 1. It means abelian group of order 10 is cyclic. Similarly, abelian group of order 15. 15 can be written as 3 into 5. This is P, this is Q. GCD of PQ is 1. Okay. Then abelian group of order 15 is cyclic. Okay. Now, this is the complete proof of Cauchy theorem, and this is the example related to the Cauchy theorem. And next class we will prove fundamental theorem of homomorphism, second fundamental theorem, related example to the fundamental theorem. Okay.